Three-phase half-wave converter. Three-phase half-wave converter provides high average output voltage, and in addition, the frequency of the ripples on the output voltage is higher compared to the single-phase converter. As a result, we need a filtering. For these reasons, three-phase converters are used extensively in high-power variable speed drives. This is our three-phase half-wave converter circuit. Since it is a three-phase, we have a VAN is going to start at 0 degrees, and the phase shift between each is ABN is going to start at 120 degrees, and VCN is going to start at 240 degrees. Now, let us represent this in the waveforms. This is VAN. VBN. VCN. T1 is connected to VAN, T2 is connected to VBN, T3 is connected to VCN. So we can turn on the thyristor T1 when VAN is positive. That means we can turn on this thyristor at this time, pi by 6. So we can turn on the thyristor after pi by 6. And T2 is connected to VBN. So it can be turned on after this value. 30 plus 120, it is 150. So pi by 6. T3 is connected to VCN. So T3 can turn on when VCN is positive at 3 pi by 2. Firing angle given to T1 after 30 degrees, and firing angle given to T2 after 150 degrees, and firing angle given to T3 after 270 degrees. Then T1 can be turned on at alpha pi by 6 plus alpha, and for T2 5 pi by 6 plus alpha, and T3 3 pi by 2 plus alpha. T1 at an angle alpha, let it be. This is my alpha. When I turn on the thyristor, this is my output across the load. We have considered the highly inductive load. Then the negative peak arises, and T2 can be turned on from this area. Then this is the output. When T2 is turned on, across the T1 there is negative voltage, and due to the inductor that negative peak comes, but due to the negative voltage, T1 is going to commutate and gets off. That is known as line commutation. Then T2 will continue on the negative until the T3 is turned on. Now the T3 is turned on after 3 pi by 2 plus alpha. This is a positive value. Then this is my alpha. So this is turned on at here. This is the output. This negative peak comes due to inductive load. Then this is again T1 is turned on here. So this is my output. So output voltage is then if I redraw that, the output voltage V0, this is due to T1, due to T2, T3, T1. So T1 is again repeated. So before T1 there is a T3. So I'm drawing that T3. This is our output. Now the currents. This is total current is available between pi by 6 plus alpha to the next thyristor turns on here. This is due to T1 from here to here. This is due to T2 and here to here. This is due to T3, again T1. Before T1, it's T3. From this, we can say the output voltage is continuous. This is our output voltage I0. As the firing angle is alpha, T1 is turned on at pi by 6 plus alpha, and it continues to conduct until T2 turns on, and T2 is going to turn on at 5 pi by 6 plus alpha. Then it's going to continue with conduction until T3 turns on, and T3 is going to turn on at 3 pi by 2 plus alpha, and this is going to turn off, and again T1 is going to turn on. So this cycle repeats continuously. As the inductive load is there, it is a continuous conduction. Now let us find out the average output voltage for this, that is VDC equals to, we can see 3 times the voltage is repeated within the period of 2 pi. The integral, the voltage is via sine omega t and d omega t. And this is the limits between pi by 6 plus alpha to 5 pi by 6 plus alpha. If you solve this, 3 Vm by 2 pi, sin alpha is minus cos alpha, so minus cos omega t within the limits pi by 6 plus alpha, pi by 6 plus alpha. 3 Vm by 2 pi, I'm taking this minus out, so cos 5 pi by 6 plus alpha minus cos 5 by 6 plus alpha. Now to solve this, 3 Vm by 2 pi cos 5 pi by 6 cos alpha minus sin 5 by 6 sin alpha, then minus cos 5 by 6 cos alpha, minus of minus plus sin 5 by 6 sin alpha. These two terms, let's cancel. 5 by 6 is nothing but 150 degrees of cos, that is minus root 3 by 2. This is root 3 by 2 minus minus plus, so 2 times, that equals to 3 Vm by 2 pi of a minus of minus plus again, so root 3 by 2 of 2 times cos alpha. We'll be getting 3 root 3 Vm by 2 pi cos alpha. This is nothing but VDC. Now normalized voltage, that is Vm, is given by DC by maximum value of VDC. The maximum value of VDC is when cos alpha equals to 1, 3 root 3 Vm by 2 pi. Then this one divided by 3 root 3 Vm by 2 pi is given by cos alpha. RMS value, that is V RMS equals to 3 by 2 pi integral pi by 6 plus alpha to pi by 6 plus alpha Vm square sin square omega t d omega t whole to the power of 1 by 2. 3 by 2 pi Vm square, and taking this out, omega t by 2 minus sin omega t by 4. 5 pi by 6 plus alpha, 5 by 6 plus alpha. Then 3 Vm square by 2 pi of 5 pi by 6 plus alpha minus 5 by 6 minus alpha minus divided by 2 sin 5 pi by 6 plus alpha minus sin 5 by 6 plus alpha divided by 4. If you simplify this, then you are going to get V RMS equals to root 3 Vm 1 by 6 plus root 3 by 8 pi cos 2 alpha whole to the power of 1 by 2. Formulas use. In cos, if it is plus, it is minus. If it is minus, it is plus. In sine, plus is plus, minus is minus. These are the formulas used while deriving the above equations.